Good morning. Let's begin. Any more homework assignments? All right. We have an exam on Thursday. Today's Tuesday. So what I'm going to do is, instead of giving that to the grader, and it's sometimes 1 week, I'm going to grade it as quickly as I can this afternoon, just mainly looking at if you have the right answer or not. And I'll put those in the box that's outside my office door as soon as I'm done grading them. I'll send out, well, you'll see the scores online when it's finished grading. So you can collect those papers once you see the scores are online, and hopefully that'll help you to prepare for the exam that we're having on Thursday. Any questions before we begin about dimensional analysis? At the end of class, I have to save a little bit of time because today at the end of class we're going to do our survey of outcomes, and you've probably seen these before where topic by topic you identify whether you feel like you've learned the material. Okay, well, let's get into it. The first thing from Chapter 8 that I want to tell you about today is a concept that's called dimensional homogeneous. And most, if not all, of the equations we've looked at this semester are dimensionally homogeneous, in that what that means is the equation has the same units on both sides of the equation. So let's take, for example, this formula, which you'll see again next semester. We haven't talked about it yet this semester, but you'll see it next semester when you talk about flow over a weir. So if there's water flowing over the edge of some barrier, then this equation can tell you how much water there is. What's the flow rate? And it's based on, let me just do a little sketch on the board here to give you an idea of what we're talking about. So if here was a rectangular channel, water's flowing over the edge of that rectangular channel, maybe because there's some sort of a block in the way. And so water is rising and rising in the river, and then it flows over the edge. So this formula says that if you know the length of a weir, which is how wide the channel would be in this case, and if you know h, which is the height of the water above the edge that it flows over, then you can calculate from those two parameters what's the flow rate. This formula says it's 2/3 c, and c is just sort of an energy correction factor that tells you how much energy loss there is as the water flows over that edge. And c itself is dimensionless. And so let's look at the units of each term of the right side of the equation and see if it matches what we expect on the left. So the length, which is the width of that weir, has units of length, meaning meters. Okay? Inside of the square root term, you can see there's 2g. And g has units of meters per second squared. So that's inside of the root term. And then h would be the height of the water, and you measure that with meters. And so now what we're talking about is meters to the 3/2 power. So that's to the 1.5 power. Okay, so we have, if we add it all up, meters to the first, meters to the 1/2, and meters to the 1.5. And so cumulatively, that's cubic meters. And now you can see that the seconds is squared, but that's inside of a square root, so that just takes it to seconds. So combining everything together, on the right side of the equation, the units are cubic meters per second, and we already know that Q, flow rate, should be measured in terms of cubic meters per second. So this is an example of an equation that is dimensionally homogeneous. And usually, equations that are dimensionally homogeneous have their foundation in the fundamentals of science. You know, it's based not just on empirical observation, but on a known law, a physical law. In contrast, we have empirical equations, which is just where data has been fit to some curve. And so you maybe have had the experience in a lab report, something like that, where you had on one axis some characteristic, like maybe it would be depth, and then on the vertical axis you would have flow rate Q. And then you just had a bunch of data points, and it's not that you know anything about the true relationship between these two, but you just tell Excel, do a best fit curve. And so Excel maybe does linear, logarithmic, exponential, a power relationship, you know, whatever formula. You can keep trying different ones until you hope magically somehow the curve fits the data well, and it'll tell you the r squared for the best fit and maybe gives you an equation. That's an example of an empirical relationship, and oftentimes when you have a formula that's based on an empirical relationship, it's not dimensionally homogeneous. And so an example of a non-dimensionally homogeneous equation, Q equals area divided by n, area divided by wetted perimeter to the 2/3 power, slope to the 1/2. This is something that's called Manning's equation, and you don't need to know Manning's equation this semester. You're going to use it a lot next semester. But it's an example of something where they took some roughness factor n, and they're hoping to predict the flow rate based on channel geometry, like the width of the channel, the depth of the flow, how steep is the channel going downhill. And if you were to combine all of these units together, then you'd find that in and of itself, this equation is not dimensionally homogeneous. That is, the right-hand side units don't match the left-hand side units. So that's just one concept that you should keep in mind, is the idea of dimensionally homogeneous. We're having to skip through Chapter 8 pretty lightly since we've just got one day of class to look at the topics. And so there's a lot more detail that maybe someday in graduate school you'll learn a lot about dimensional analysis. But one of the main ideas is this one about dimensional homogeneous equations. So here's another thing that we're going to talk about. And it's the idea in dimensional analysis that sometimes you use a small thing to predict what's going to happen with a big thing. And the small thing is called a model. The big thing is called a prototype. So where are models used to simulate a full-scale object or scenario? In the case of a wind tunnel, where you have a model of an airplane, you could put a model that's carved from wood, or sometimes they use clay to prepare models. And putting it in a wind tunnel would allow you to do lots of different changes to the wing. If you're trying to find out making the wing longer or shorter or thicker, what effect does it have on the airflow over the wing and how much lift can be generated? Think about how much easier it is to make changes to a clay model compared to building a full-size airplane anytime you want to make and test some small change in the wing. And so it's a lot more efficient to make changes to a model than to constantly have a full-size prototype. And so that's an example of why models are used to simulate a full-scale object. And maybe if you've ever watched a TV show called Mythbusters, have any of you seen that or heard of it? It's something where they a lot of times before they do a full-scale test, they'll make a small model of something just to see in concept if the forces work out like they predict it's going to be. So the question is, in dimensional analysis, is how big should certain things be to get an accurate representation between the small object and the large object? And so what I mean by that, an accurate representation, is think about a small model car, like a toy that you would get in the store. Those small models that are maybe just 3 or 4 centimeters long, if you drop it from waist high onto the floor, it's okay. You can pick the toy up and it wasn't crushed. It didn't explode. But if you think about lifting an actual car to the equivalent height based on its size, so a small toy that's this size, if you lift it up to your waist and drop it, it's fine. But think about lifting a full car, maybe 50 stories, and then dropping it. It wouldn't survive in the same way that the model does. And so that's an example of how a model actually isn't representing what happens in the real world very well, because in the case of toy cars, the toy cars are too strong. And so it's not an accurate simulation to use a toy car to a real car as an indication of what might happen. And so there's a procedure we can go through to find out if you want to have a realistic interpretation of the forces and the impact and all of the parameters that you want to test, you have to scale things appropriately. Here's a picture of a hydraulic model in San Francisco that's used in a similar way. This is a physical model for the Bay Area. And in San Francisco, they have a very large bay that has many rivers coming into it. On one side of the bay is the ocean. On the other side is a lot of rivers that come into the area. There's shipping traffic. They've done a lot of construction along the coast. And many years ago, they realized that all of the changes that they were doing to the bay risked the environmental aspects of it. That there might be erosion, that the tides could be changing because of how they put dams on the rivers. The fish habitat could be threatened. And so they built this model so that they could make changes to the model and then see what happens. They could measure the flow rates through sections of the model. They could see how the current patterns were changed. And so this model is very large. The size of it is about 100 meters wide and 120 meters long. Here's another picture of it from a different angle. And so they have water flowing in all of the locations that in the real world there's also flow in. And they can, with sensors inside of this tank, measure in a way that's even more sophisticated than they could build a computer simulation for. And of course, there are computer simulations that will do the same thing. But a computer simulation is only as sophisticated as we know how to make it. And this, because it's a physical representation, it's not limited by how clever is the programmer. It's not limited by the computational horsepower of the mainframe that it's running on, but it's a physical representation of what's really there. And here in the UAE, they've built a lot of new things along the coast. In Dubai, for example, there's the Palm. They're making the World Islands. And those changes that they've made have affected the erosion patterns along the coast. Beaches that used to have sand that was stable, now they have to have a stockpile of sand to the side of the beach so that they can always be bringing more sand when the tides are eroding it, because they've changed the flow patterns. And so models like this can help you to understand how changes are going to affect existing coastlines, just as one example. And so modeling is very useful and important. The principle of using a small thing to predict a large thing is called similitude. Similitude means it sort of sounds like similar, the word itself. And geometric similitude means that you've scaled things just based on a ratio of the dimensions. And if you are into building models, there are models of cars and airplanes and boats where when you look at the packaging of the model, it will tell you maybe 100 to 1, meaning that 1 centimeter on the model is equal to 100 centimeters of the real thing, the prototype that it's trying to simulate. And so here on this drawing, you can see that we have some length of the prototype. This looks like a boat. And so the length of the prototype, and here is the model, the smaller object. We have the length of the model. So if we made a ratio of the length of the prototype and the length of the model, we'd get some factor, and all of the other parameters are scaled in the same way. And so the length to the length ratio here, maybe just from looking at it, maybe it's 2 to 1. And so that means that the width of the model should be half of the width of the prototype, that the distance from the stern of the ship to the passenger cabin, if that's what this is, all of the distances should scale similarly. Now this is just geometric similitude. Having geometric similitude doesn't ensure that the model and the prototype are going to behave in a similar way, though. Remember when we were talking about the example of the toy car, dropping the toy car and it's artificially strong. So you actually need to think about not having a similitude of the dimensions, but really what you need is a similitude of the forces, dynamic similitude. And it's dynamic similitude that's used in simulation of fluids acting over, for example, the spillway of a dam. That's what this diagram is showing, is there's water behind a dam, and then it flows over the top of the dam, and then it's cascading down a spillway and eventually goes to the river that's downstream. This is a really important situation for hydraulic designers because the water is moving very fast at the end of the spillway because it's falling so far. And so there are a lot of physical models and computer models that are simulating this thing to try and find out what's the velocity of the liquid, and cavitation is an issue in spillways, and so they'll try and analyze the interface between the water and the spillway to find out what is the water pressure to make sure that those little bubbles don't start to form from cavitation, because those little bubbles can cause erosion of the material, can cause a lot of damage if it gets out of control. And so what they do to achieve dynamic similitude is you make sure that the forces for the large one correspond to what the forces should be for the small one by matching the Reynolds numbers. Now, you remember Reynolds number is one of the things we've used before to characterize a flow as turbulent or laminar. And one way to calculate the Reynolds number through a pipe is the velocity times the diameter of the pipe divided by the kinematic viscosity of the fluid. And so what they would do is, for the large scale item, they'd find out what is the velocity of water that's going down the spillway. Now, in this case, there isn't a diameter because this is open channel flow, but instead of diameter, they'd use some length parameter. Maybe they're talking about the height of the spillway. And so how high the spillway of the model needs to be, you would match the two Reynolds numbers together. So you'd calculate the Reynolds number for the prototype, and you'd make it equal to the Reynolds number for the model. I'm going to show you an example of what I mean by that. Sometimes, actually, let's go to the example and then we'll come back to this slide. So here's an example of a blimp. Maybe you've seen pictures of things like this before. They fly over stadiums during events, and so let's say that the full-scale prototype is going to be 60 meters long and 5 meters wide. And we want to study what happens in the real world with this by having a smaller scale model inside of a wind tunnel. And the model is 1 to 10, meaning that instead of 60 meters long for the prototype, how long will our model be? 6, exactly. So it's going to be 6 meters long and 0.5 meters wide. That will be our model. The prototype is going to fly at 10 meters per second. And so the full scale item will fly at 10 meters per second. And so we want to find, for example, what forces are going to be acting on the front of the prototype in the real world. And we're going to be testing that in the wind tunnel with our model. And the question is asking here, what wind speed should we use in the wind tunnel? So let me show you what procedure we use for solving a problem like this. In the concept of similitude, dynamic similarity means that we want the Reynolds number of the model to equal the Reynolds number of the prototype. All right, so the Reynolds number of the model should equal the Reynolds number of the prototype. And I just wrote the Reynolds number previously in terms of velocity, diameter, and kinematic viscosity. Here's another formulation of the Reynolds number. The Reynolds number can be the velocity, some length parameter, the density of the fluid, and then the absolute viscosity instead of the kinematic viscosity. Remember, the difference between the two is that kinematic viscosity is absolute viscosity divided by density. Okay, so this is Reynolds number. What we're going to say is that the velocity of the model, the length of the model, the density of the fluid that's used for the model, and then the viscosity of the fluid that's used for the model, all of those things together should equal the equivalent for the prototype. So velocity of the prototype, length of the prototype, density of the prototype, and fluid viscosity that's used with the prototype. So we want to set all of those things equal. Now here the unknown is, what wind speed should be used in the wind tunnel. The wind tunnel is the thing that we're using with our model. And so the unknown is V sub n. So we need to rearrange this equation to solve for V sub m. The velocity of the model is going to be the velocity of the prototype, length of the prototype, density of the fluid of the prototype, viscosity of the model divided by viscosity of the prototype, length of the model, and density of the model. Okay, so I've just moved that to the numerator and these two to the denominator, and we're left with some expression that's going to allow us to calculate the velocity of the model. So let's put in all the parameters that we know. In this case, air is being used for both the prototype and the model, because it's saying what is the wind speed that should be used in the wind tunnel. So it's air in both places. So since it's air for the model and prototype, what does that tell us about the viscosity for both fluids? Well, they're equal. They're the same. We could look up the viscosity if we wanted to, but since the viscosity of the model and the viscosity of the prototype are the same, it's just easier for us to cancel them out of the equation entirely. And so the viscosity of the prototype equals the viscosity of what's used for the model. It's air in both cases. And the same thing is true for the density of the fluid. The density of the prototype fluid is equal to the density of the model fluid. Now, that's not always the same, but in this case they're the same. So we can cancel out the density term as well. And so when we actually do the substitution, we have the velocity of the prototype, and it says in the problem statement the prototype is going to go 10 meters per second. So we have 10 meters per second. And now the length parameter for the prototype, we could say 60 meters, or we could do 10 to 1. Let's just say 60 meters. And then the length of the model is going to be 6 meters. So what we know then is that inside of the wind tunnel, we should make the air go 100 meters per second. So think about what that means. The model is smaller. We're saying if we want to test what happens with this full-scale item, and we have a small model that we're testing in the wind tunnel, you shouldn't have the wind moving slower than it's going to in the real world, but actually you should have the wind moving faster than it should in the real world. In the real world, the wind will be moving 10 meters per second. And so maybe if you didn't know about this similitude, you'd say, since it's 1/10 the size, the wind should be moving 1/10. But why do you think it's actually 10 times faster for the wind instead of 1/10? It's about the forces, right. And a thing that's small resists forces more easily than a thing that's large. And so we need the wind to be moving very fast over that small object so that there's a dynamic similitude. So this method will never guide you in the wrong way. You can always use this dynamic similitude method for the types of problems you're going to see that are asking you for a size scaling difference. So let's go back to this slide that I jumped over before. Sometimes the fluid velocities are too high. Here, for example, 100 meters per second. Maybe we can't do that in our wind tunnel. The fan might not be able to achieve a speed of 100 meters per second. So what this slide is saying is, instead of using a really high wind density, you could actually change things around a little bit. You could pressurize the wind tunnel to increase the air density. So we were assuming that the viscosity and the density were the same, but if we adjusted one of those two, then we wouldn't have to have the wind speed as high. Like we could use air for our prototype, but for the model we could do compressed air. And if we did compressed air, then maybe we wouldn't have to have it going at the velocity of 100. Or even we could change fluids entirely. We could use air for the prototype, but for the model we could use water. And we could find out with water that has a higher density and a different viscosity, we could find out how is the air going to affect the prototype by using a non-air liquid for the model. So you can change things around, and sometimes in simulations they'll use different fluids just because it becomes easier for them to take the measurements that they need. Any questions so far about what we're talking about here? Similitude? All right, I just realized that in the recording it's not going to show up what I wrote on the board. So here's that blimp example that I had before, where we were relating the model and the prototype and end up with a velocity of the model of 100 meters per second. All right. I'd like you to try this out at least one problem through the semester. You know, we don't have a homework assignment with Chapter 8, but I do have an example I'd like you to try here in the class. So do this pipe flow example. The situation is that we have a model and a prototype. The oil flowing through this 15 centimeter pipe is going to be our prototype, and we want to model it with a 5 centimeter pipe that's using water. Let me just tell you that the viscosity of water, let's use a kinematic viscosity of water, is 1 times 10 to the minus 6th meters squared per second. So set it up in the same way where you have Reynolds number of one equal to Reynolds number of the other, and try and find out the velocity of the water. Velocity of the water is the unknown. So if we want to have the forces that's on the inside of the pipe, remember that when water is flowing through a pipe, or any fluid is flowing through a pipe, if the water's going this direction to the right, then the pipe is resisting the flow. So what this correspondence is going to do is it's going to say if you have oil flowing through a big pipe and you want to simulate what the forces are going to be like for water flowing through a small pipe, and you know the velocity of the oil is going to be 2 meters per second, then if you want to have the same scaling of forces, then you should have the water flowing at 1.5 meters per second. And so that's the main idea behind dynamic similitude. Pretty straightforward, right? All right. Are there any questions about what we've talked about as far as similitude or modeling goes? Yes? Mm-hmm. Yep.
Is it possible to, like, simulate turbulent flow or certain fluid?
So,
It's already like you can't.
So, okay, the first thing you're mentioning is that we use Reynolds number to distinguish between laminar and turbulent flow. Laminar is when it's below 2,000, turbulent is when it's above 4,000. Now this works, this scaling of model and prototype, it works regardless of whether flow is laminar or turbulent. So you can use it in either circumstance. And so your question was asking...
Can we represent the turbulent flow? Because it's already like...
Right. So there, in turbulent flow, there's a lot of random behavior, right? Yeah. And so if this is still going to give you accurate scaling, because if you had turbulent flow in the oil pipe, for example, you're also going to have turbulent flow excuse me, in the water pipe. So it's good to keep in mind that there's a lot of random and unpredictability when you have turbulent conditions, but this scaling does account for that. Okay. So all we've got left for today is this survey of outcomes. Let me just remind you one last time that the exam begins at 8 o'clock on Thursday. If you come late, this is the one time in the semester that I don't mind if you come in late. Come for the exam at 9:30 if you wish. It's up to you. Sleep in. Take it easy. But you won't have any longer to take the exam. The exam will be done at 10 o'clock on Thursday. All right. How many questions? Can you believe what a procrastinator I am? I haven't written the exam yet. I was busy writing grading quizzes, and so I'm going to prepare the exam tomorrow. Approximately? Okay, well, you won't hold me to it, but you just want a rough idea, right? Okay, typically what I do is for our 50-minute exams, 3 questions, right? So the equivalent, I'm trying to make maybe 5 questions for 120 minutes. But maybe I would make 6, but then 2 of them are very small questions. But roughly speaking, it would be 5 of the same kind of questions that normally you're getting 3 of. And so you're having a lot less time pressure than you do for the midterm exams. There may be theory questions. Since I haven't written it yet, it just all depends on when I look over the material. Like I have to review what questions I've already given you, and I have to ask, do I want to give you a repeat or something different? It's a lot of factors to consider. Yeah. Okay, so on this survey I'm going to give you, 5 means that you feel like you've learned it. 1 means you feel like you didn't learn it. And then there's everything in between. And so it's asking, please indicate your level of agreement with that this course has enabled you to do something. So if you feel like you didn't learn how to do something in the course, then you should choose on the right side. If you feel like you did learn how to do it, then you choose on the left side. You don't need to write your name on these. These are anonymous. So no need to identify yourself. Let me just turn off the recording here.